Okay, 8th grade, welcome back. This is the start of our next chapter, which is on magnets and magnetism. So you probably have had magnets at some point in your life that you've played with. They can be a lot of fun. And so we are going to be looking today at what it is, how it works, all that good stuff. Now, before we do that, there were some review questions on your paper that you were supposed to answer about electrostatics. So what is electrostatics? Remember, that has to do with stationary electric charges, charges that are like building up on the surface of an object. We talked about how atoms have protons, neutrons, and electrons. Protons have a positive charge, neutrons have a no charge, and electrons have a negative charge. Most of the time these are balanced out, and so atoms may not have a stronger electric charge. But sometimes they do. And you have more protons or more electrons, and that creates one of those positive or negative charges, which is also the answer to question 2. What are the two types of charges? Question 3 was about the two laws that we learned, the law of electric force and the law of electric charge. And those we're actually going to kind of revisit again today, because magnetism and electricity are really two sides to the same coin. They are interrelated with each other, and both of those laws, actually, you're going to find out, are very, very similar to the same laws in magnetism. So just to review from your notes, you should have read your textbook, pages 326 to 330. If you haven't done so already, go ahead and stop this and go ahead and read that and come back to us. All right? Magnetism is the property of attracting objects by magnetic force. That's your first blank, okay? And you've seen that when you've used magnets before. You've seen this attraction that happens between the magnets where they want to be together and they just are attached, right? That's an attraction that's there, okay? It started with sailors a long time ago. They used what we call lodestone. And lodestone is essentially, it's black iron oxide, which is magnetite, okay? And it is, it's just always been known for its mineral properties, or magnetic properties. And so what they would do is they would take a piece of it, and they would, sorry, I'm on the wrong page in my notes. They would let it float in a bucket of water or suspend it on a string, and that it would always point north. And so they would use that as a way of figuring out how to go which direction they wanted to go, because it would point them towards the north. Okay. Perleon, which is someone who worked with this magnetic force a lot, he called the pole that points towards the north-seeking pole, and the pole that points towards the south-seeking pole. So when it would point towards the north, we call that the North Pole, which we're going to talk about poles right now. So in your notes, the law of magnetic poles states that like poles repel and unlike poles attract. Now, what does that sound like? That should sound very familiar to you, and it should sound familiar because it's just like the law of electric charge that talks about how opposites attract and likes repel. Okay, so like poles repel, unlike poles attract. And you've seen that whenever you use magnets, right? One end wants to go to the other end like this, and the other end does not. And there's like a force that pushes against it and doesn't want them to touch. Sorry if you can't see that very well. Okay? Poles are essentially just areas of increased magnetism. Okay, we're going to talk there's a picture in your notes there of the red and gray bar magnets, okay? And the poles are essentially the ends, okay? That's where you see a lot of magnetism. That's where the force is the strongest, okay? And so poles are regions of concentrated magnetism. That's the blank in your notes. It always exists in pairs. You always have a north and south. So if I were to break this magnet in half, I would still have a north and south pole. If I broke it in half again, I'd still have a north and south. As many times as I break it, you're still going to have that north and south pole. So they always exist in pairs. You will always have two poles no matter how many times you cut this magnet up. Okay? And even things like these specks, right? You've probably seen these ball magnets before. They're kind of fun. You'll see, oh, they keep wanting to attract each other. So if I bring these close together, they want to be together, right? So that's unlike poles. They want to be together. So we've got a north and south. If I take it and flip it around, though, now notice what happens. They're like trying to get away from each other. They don't want to be near each other because they are unlike poles. So, or sorry, like poles. So even these ball magnets that look don't, like they wouldn't have a north and south pole. They do, okay? Magnetic fields, I want you to look at the picture on page 327 in your textbook, okay? I would do this normally in class with you guys and have you guys do the iron filings, but we can't do that, unfortunately, so you're going to have to look at these pictures. Essentially, if you take a magnet and cover it with something clear and then sprinkle on your iron filings, you will notice that there's areas of increased magnetism, which is the poles. You also notice that it appears like there's these like lines coming out from that, okay? Those are the magnetic field lines, okay? And so in your notes it says the area surrounding a magnet in which other objects are affected by magnetism. Go ahead and pause anytime you need to or rewind to get these notes down, okay? So a magnetic field is the area surrounding a magnet in which other objects are affected by magnetism, okay? Now, you will see that if you look at those pictures, you'll see the poles have a whole lot more lines coming out from them because, again, we said poles are these areas of increased magnetism. Within that, we have what we call lines of flux, okay? These indicate the direction and strength. That is, those next two blanks indicate the direction and strength of the magnetic field. On your next page there, you should see some pictures, the pictures I was talking to you about, and you see the blue lines coming out. Those blue lines are the lines of flux, okay? They show which direction the force is being attracted to. Some are going away, some are going towards. And you see what happens when you bring a north and south pole together. You notice all the lines are there and it's strong. And then when you put the third picture where you have the two north poles coming together, you notice that those lines of flux are going away from each other, which is why you have that repulsion that happens, right? Where they just don't want to be together because those magnetic lines of flux are pushing them away, okay? All right, so the law of magnetic poles is just like the law of electric charge. The law of magnetic force is just like the law of electric force, okay? Which states that the force between two magnetic poles is directly related to the product of the poles' strength, okay? It's also inversely related to the square of the distance between the poles. Wow, that sounds so familiar. Good, it should. This is an inverse square law. And when you get to your think question, you need to use this law of magnetic force to explain it. So it's essentially, remember when I talked about in the videos before about how if I double my distance, what happens to my strength? And if I increase or make my distance smaller, what happens to my force, right? It's the inverse, the opposite, and then to the square, okay? So give that a try in your think, do your best, and I will work with you if you have some trouble with that. The last thing that we talk about in this lesson is permeability, which is how strongly a magnetic force acts through a material, okay? So the higher the permeability, the more easily it's going to be magnetized, okay? On page 329, it talks about this in a little bit more detail. And it shows how when you put a magnet inside of an object, it can make it so that that magnetic object is is not as attracted as it once was before, okay? And so you can direct, it's essentially what we call magnetic shielding. And so you can decrease the magnetic strength of something by having it surrounded by something else. So things with high permeability would include things like iron, cobalt, nickel. Things with low permeability would be things like wood, human tissue, let's see, air. Those things don't have a strong permeability. And again, look at the pictures in your text, guys, because those will help to make sense of things, okay? And tomorrow when we get on Zoom together, we'll go over this again, and you can ask me any questions. Try and do your homework before that point. And that way, if you have questions, we can go over that. And then once we're done Zooming, you can send me in your homework, and I'll grade it and get it back to you. Okay? Hopefully, we just have to do this till April. We'll see. All right. Love you guys. Bye.